temperature now and Le Chatelier's principle. Now, once again, remember Le Chatelier says, if you do something to the system and disturb the equilibrium, it wants to re-establish equilibrium. Essentially, if you increase the temperature, the system wants to decrease the temperature. If you decrease the temperature, the system wants to increase the temperature. But at the end of the day, if you change any one of these three things, the temperature, pressure, or concentration, you will affect the equilibrium position. In other words, you are changing the equilibrium of the system. Now, the question is, how does temperature change the equilibrium position? And that's what we're going to answer now. Okay, temperature. Well, it's as simple as this. An increase in temperature favors the endothermic reaction. And the contrary is also true, where a decrease in temperature favors the exothermic reaction. Now, my word, what do these things mean? Okay, firstly, let's talk about favoring. You need to now use your heads, people. You need to use your heads from the section where we talk about rates of reactions. An increase in temperature will always increase the rate. Okay? A decrease in temperature will decrease the rate of a reaction. Now, why in the world do we talk about favoring? Well, when we increase a temperature, if I have an exothermic reaction and I have an endothermic reaction, if I increase the temperature, the rate of the exothermic reaction will increase, but the rate of the endo will also increase, but will increase more. So think about this as giving people sweets, right? I've got two kids. One is exo, my other kid is endo. I give the one kid 5 sweets and I give the other one 10 sweets. Who is going to be favored? The one that obviously gets more sweets, right? So even if we give them the same temperature, the reality is it's like speeding up the rate of the one more than the other. If I talk about decreasing the temperature, the exothermic one is favored. So if I had to go into a place and I'm going to repossess or take people's money, obviously the one from whom I take less money away will be favored, right? So in other words, both rates, if I decrease the temperature, both rates will decrease. In other words, the rate here will decrease, but for the endothermic, the rate will decrease more. So of course, the exo is favored over here. With a decrease in temperature, my exothermic reaction is favored. Okay? And with an increase in temperature, my endothermic reaction is favored. Now remember, when we deal with things that are called reversible reactions, when we drew their graphs, remember that one graph looks like that and the other one will look like the reverse of that, which just looks like that, you know? That's why it looks sort of like a mirror image. This one here is endo, this one here is exo. If I have an equation, let's say it's A plus B, and that gives me in a reversible reaction C, and I tell you that the forward reaction is endo, then A plus B, giving me C, with a single arrow here, is endo, but C giving me A plus B must be exo. Okay, so in the same way that we had to look at pressure to determine which one will be favored, over here we're going to have to look individually at which is exo and which is endo in order to determine which is the reverse and which is the forward reactions. Okay, but here's the rule. Nevertheless, here's the rule. So I'm going to give you the same reaction we've been dealing with now for a while, which is N2 plus H2 gives me NH3, right? And that's a 2 and this is a 3. I have a feeling I made a mistake in the previous video. We will have to go and check that again. But nevertheless, that is, it's 1:3:2. And let's look at this over here. I have a feeling I wrote the wrong thing there, but nevertheless. Yeah, let's focus on this one, yeah. Now, this reaction is usually given with delta H less than 0. You are told delta H is less than 0. Now, when this is quoted, this tells you for the forward reaction, okay? Now, if the forward reaction delta H is less than 0, then it means the reverse reaction delta H is greater than 0. Now, firstly, that's forward reaction, and secondly, if delta H is negative, from one of the previous videos, I think it was video number 8, this tells us that the reaction is exothermic. Okay, now I'm going to ask you, what happens, what's the effect of an increase in temperature for this reaction? Well, we know by default an increase in temperature favors the endothermic reaction. And in this case, this is an exothermic reaction. The forward reaction here is exothermic, which means the reverse reaction must be endothermic. So in the increase in temperature here favors the endothermic reaction, which in this case, it is the reverse reaction. So if you want to make more of this thing, you want to produce more nitrogen and hydrogen, you can always increase the temperature because it's going to favor things in this direction. It's going to make you produce more of this quicker than what this can come together and form this thing over here. Okay? So let's look at the reverse. What about a decrease in temperature? Well, as you know, a decrease in temperature favors the exothermic reaction. Okay. It favors the exothermic reaction, which in this case is the forward reaction. So this means that I want to produce more ammonia, then I can always decrease the temperature because my forward reaction over here is my forward reaction, which I'm drawing with the red arrow. That is going to be exothermic, because an exothermic reaction is favored if I decrease the temperature. Okay, we have to talk about the practicalities of this reaction a little bit later on, because sometimes you could decrease the temperature too much that the whole operation is not fruitful, and that's not what you want, right? You want a relatively low temperature in certain instances, and that's one of the examples here. Okay.